Hello everyone and welcome to this wonderful lecture. Today we'll be discussing on the subject of digital image processing. And our topic of discussion today will be looking at the introduction and application of digital image processing. My name is Dr. Victor Mokaya from the Department of Computer Engineering and Information Technology from Suresh Gyan University. This lecture is dedicated to the seventh semester. Now, today we are going to look at the following objectives, and it is very necessary to understand what you are going to study so that you know whatever you're going to listen to, what is going to be covered. So first of all, the objective that you're going to look at in this lecture are as follows. The first objective is to introduce what is image processing. So the subject itself is on digital image processing. Now, it will be very much unfair if we don't decompose what this digital image processing is and how does it come, why is it necessary, and how does it develop, how does it come about. So from the first objective, we'll be able to describe other two objectives. The first one is sampling, and the second one is quantization. So we'll look at what is sampling, and what is quantization, and what is the relationship that exists amongst the two of them. After that, we'll now be able to see what are the applications as well as the prospects of digital image processing in current day scenario. So it is very necessary to understand that whatever we are going to cover today must have a real life application in the industry or different application environments, so that we know that whatever we are going to cover today does not only stick on the paper, but also can be applied and make lives better. Now, having covered these objectives, these are the outcomes that you need to understand after the lecture is over. So the first outcome that you need to understand is to be able to differentiate what is a digital image, what is a digital system, and what is a module. So all these are related to each other, and you need to very much understand what they are. Then the second outcome that you need also to understand better without any confusion is sampling and quantization. These two need to be understood very clearly, and that is what you're going to do in this lecture. So don't worry, we're going to discuss each one of them independently, and I believe by the end of this lecture, you'll be able to understand it. And then the last outcome that you need to know is the basic application areas of research where we can be able to apply these concepts. So those include such as in military environments, in space exploration, and most commonly in photography. So it's an interesting subject because you get to understand what is happening on your smartphone whenever you take photos and you apply filters. Now you know what is happening behind the scenes. Now let us dive into our discussion for today's class. So this is the syllabus that we'll be using for the course of study. So we have 5 units, and these 5 units, each one of them has been given a different area of coverage. And what you're going to look at is that now we'll be discussing on the first unit, which is now the introduction and fundamentals. So you can see we'll be covering on various aspects such as motivation and perspective, the application components of image processing. We'll also be looking at different enhancement techniques such as spatial domain, as well as we'll also be looking at other concepts such as image subtraction, filtering, as well as different filters. So these are the introduction as well as the fundamentals. So the objective that you need to remember for this subject, and before we come to the objectives, it is important to mention the prerequisites. When I mention the prerequisites, I'm referring to basic knowledge or basic skills you need to have to possess so that you can have a better understanding for this subject. First, you must have studied artificial intelligence. Secondly, you must have studied microprocessor and interface. You need to have studied, or if you're not studied, you should be studying on a parallel. It should be one of the subjects that is being offered to you. So switching theory and logic design. So all these four subjects, or these four technologies need to be understood by you in prior before coming to this lecture. So the objectives we'll be covering are: one, the fundamentals of digital image processing. The second objective will be image transform used in digital image processing. Third, image enhancement techniques used in digital image processing. Fourth is image restoration techniques and method used in digital image processing. And lastly, we will cover on image compression and segmentation. So all these techniques are very wonderful techniques to cover. And now that we have data science and machine learning and artificial intelligence, these technologies very much use these concepts. So everything is not going to waste. These are techniques that you learn and you'll find them. You'll find a place for their application. The first unit will be introduction and fundamentals. The second unit will be image enhancement in frequency domain. So, and the third unit will be on color image processing. Fourth will be covering on image registration. And the fifth unit will cover on feature extraction. So this subject is basically interested in area of deep learning known as computer vision, where we are able to manipulate and on images as well as on video frames. So these are the reference books that we'll be using. I recommend this first book by Rafael C. Gonzalez and Richard Woods. It's a very wonderful book, and if you can be able to get it in either hard copy or soft copy, then this is your arsenal in understanding these concepts very much better. If you don't get it, I'm sure the University in Central Library has this book, and you can go there and you can also find the resources that are available there. So we'll be using the second edition of this book, which is published by Pearson Edition Education, year 2007. The second book I recommend is by R.J. Scaff, Digital Processing and Computer Vision, which is published by John Wiley and Son. So this is for the year 1991. Third, we'll be looking at A.K. Jain, who has published the book Fundamentals of Digital Image Processing. So from that book, we'll be able to cover similar concepts. So this one is published by Prentice Hall, Upper Saddle River in New Jersey, year 1989. On successful completion of our coursework on this subject, these are the outcomes that we need to cover. So these outcomes are not necessarily inclined for this subject only, but the entire syllabus, the entire course of this subject. So first outcome is to be able to have the ability to apply knowledge of mathematics, science, and engineering. Second outcome is the ability to design and conduct experiments, as well as to analyze and interpret data. So this is where now data science comes in. Now the third outcome should be the ability to design a system, component, or process to meet desired needs within. The next outcome will be realistic constraints such as economic, environmental, social, political, economical, ethical, health, as well as safety, manufacturability, and sustainability. Next will be to understand the ability to function on multidisciplinary plans. So we should be able to apply this concept on multidisciplinary environments. Then Next outcome is to possess the ability to identify, formulate, and solve engineering problems. Next, have an understanding of professional and ethical responsibility. So this subject does not groom you only with technical skills, it also grooms you with social soft skills such as being responsible and accountable for every action that you do within your working space. Then the last object or outcome will be to have the ability to communicate effectively. So here is where again soft skills do come. So I believe by the end you'll be able to have possessed these outcomes. Now, in this class, we'll be looking at, we are now going to start on the introduction and fundamentals. So this is the first step towards understanding what you're going to cover today. And the first, fundamental you're going to look at is what is an image. Now, I believe you've covered, you did science while you were in class 2 and in primary, and you were able to understand or to have an introduction to what is an image. So by definition, an image is a two-dimensional signal that can be observed by human visual system. Now, when we mention two-dimensional, whenever we represent any object, we have a Cartesian plane. A Cartesian plane has two axes. We have the horizontal axis, which is also known as the y-axis, and we have the vertical. So we have the vertical axis, which is also known as the x-axis. So these are the two axes that we use, and from there we represent an image on the x and y-axis. Hence, it is known as a two-dimensional. Now, the signal here. Signal is an input that is received from a sensor. So in this case, we use a camera to capture an image. And this camera consists of a lens. This lens will be able to capture the object outside, and then this object will be converted into a signal, and that signal will now be processed by the internal components of the camera, and then we'll now be able to get our output as the captured image. So the image is a two-dimensional signal that can be observed by a human visual. This one can also work with a machine visual system or also a human visual system. Next, we will look at digital image. Now, a digital image is now the image that we have captured and we want to represent it in terms of sampling. We want to represent it by sampling in the form of time and space. So here we use the two techniques, that is time and space, to represent the image. Then we have the digital image processing. So a digital image processing is to perform digital signal processing operations on digital image. So here the keyword is digital signal processing. We mentioned that this image is basically a signal. Now, when we convert this signal and represent it by sampling in time and space, it is referred to as a digital image. So when we combine both this digital image and now the signal processing, come up with the digital image processing. So that is it. So now let us move forward and now understand what is sampling as well as what is quantization. So I'll keep these very discrete and very simple. Sampling relates to coordinate values. Now, what are these coordinates? Now, we've said we can represent this image in a two-dimensional space. And we say this two-dimensional space is basically the x and y axis. Now, this x and y axis is drawn over a plane. And in that plane, that space within the region within the x and y axis is what now consists of coordinates. So any region in which we can mark any value, or we can place any value, that value within the x and y axis will consist of two coordinates. That is the coordinate on the x-axis and the coordinate on the y-axis. So whenever we perform digital image processing and we want to perform any processing that relates to coordinate values, that is known as sampling. Now, on the flip side, when we want to perform this processing on an image, and what we apply in this case is intensity value, then that is referred to as quantization. Now, you must be asking yourself, what are these intensity values? Whenever we are representing intensity values, we don't use the x and y axis. What we use is the sine and cosine. Or other words, what we use is that we try to represent this image in a frequency form. Okay, so this frequency form will have now different values depending on the color of the image. Where we have brighter patches, we'll have lower frequencies. Where we have darker patches, we'll have higher frequency. So if it is forming something like a curve, it will now be like this sinusoidal wave will be higher. The amplitude will be very higher where we have dark patches. The amplitude now, that is the height of that curve or that wave. So this wave will be lower where we're having brighter patches. That is the simplest and basic definition of what sampling and quantization is. So I expect you guys to really remember these two techniques, because we'll be using them concurrently in the course of this lecture. Now, moving forward, we look at now how an image is formed. Okay, so what occurs is that first of all, let us mention what are the requirements for image formation. One, we need an energy or lighting source. Okay, this lighting source can be any artificial light or natural light. So if we talk of natural light, we can talk of sun. And if we talk now of artificial light, you can talk of the tube or the lamp. Then the next thing we need is a scene element. This scene element is basically an object through which we want to capture image from it. The third requirement we need is an image system. This imaging system can either be actually the human eye, or it can be a camera. So this camera is basically an image system. Now, having said that, inside this imaging system, then we have other background activities that go. So we have the image that is received as it is from the scene, and then we have now the processing of the image so that you can be able to fill the requirement form that is needed for understanding and interpretation. So now let us now see how the steps are performed. So each of these objects have to be placed strategically. So the first step is that this lighting source will shine over its light to the object, which is now the scene element. Now this object, when it is shined over, now this imaging system, since it has a lens, it will be able to see this object, okay? So once it sees this object, then it is able to capture it. Take an example of how when we are in the dark, when it is night, even if you are taken outside and you are asked, now there is a coin I've dropped on this ground, on this floor, then search for it. It is very impossible. Why? Because you cannot, as much as your eyes can see, you cannot be able to see on the object because there is no light shining on this object. So that is why we need this energy source, and then the energy source has to shine on the object, and then from the object, what will happen is that now be able to, the imaging system will now be able to capture it, and after it captures it, so if it is in the camera, it will capture it using the lens, and if it is in the human eye, then the human lens will capture the object, and then it will be taken to the retina for processing. So in this case, on an imaging system, so we have now the internal components. So internal components of this big camera, it has an image plane where the image, when it is captured, it will be reflected upon as it is. Once it is reflected, now it will be able to convert this image and now be able to represent it according to its color scheme. So if it is now in the central part, we have brighter patches. Then as we move outside, we have gray, and then darker patches. All these will be represented, and then we'll get our final digitized image. Now that is the process of image formation. And this image formation can now be converted into an equation. And this equation is given by f into x comma y, which is now the output of the digitized digital image. So digital image f into x comma y. So this f refer to reflection or reflectance. So this is given by now this reflectance. So reflectance is now what is captured from this object after reflection to the imaging system times now illumination. Illumination is now the amount of light that hits this object at a particular point. So you can see this direct source hitting this point is very brighter. But since this light cannot get to this point, that is why it is very darker. So whenever we want to calculate this digital image, we have to put into perspective the reflectance as well as the illumination. Yeah. So the reflectance is always in the range of 0 to 1, and illumination is from 0 to. Now, we've said before that in sampling, we are more interested or focused on the coordinates, while in sampling, we are more focused on, in quantization, we are more focused on the intensity. Now, this is a diagram that we use it to indicate the different activities that occurs in an image. So we have 4 figures. This is the first one, then the second one, third one, and last one. Now, a general digital image is shown by this A. So this is a general image that has been digitized using an image source. Then the next step is that this image can also be referred to as a continuous image because it is fully as it is when it was captured by the imaging system. Then in the next step, we have a scale line from A to B in the continuous image. We have this scale line from A to B. This scale line is there so that it can be able to assist us to convert this image into either sampling and quantization. Why is that necessary? Because as you see, as we move from A to B, we have regions that are darker, where I'm pointing, and we have regions that are slightly darker or brighter, and then back to darker patches. By so doing, this scale line helps us to represent that. Now, so we will use it to illustrate the concept of sampling as well as quantization. So in this image, we have the first step. So let's take an example of this image here. We said sampling is basically involving what? Coordinates. Now, you can see on this point here, we have very bright patches. Okay, so these bright patches, that is the region outside the image, is, you can see like the coordinates here are very high. Same thing occurs to point B, the coordinates are at a higher level. But now when we talk of now this image at the center, you can see at the bottom here where now it is the boundary, the lowest point where it is extremely darker. As we keep on moving to the center, also our graph here keeps on increasing. So by increasing, it means that the coordinates keep on changing. Okay, so we can so do this by now selecting the coordinates values, and those coordinates values are what now help us to be able to describe this image using quantization sampling. Okay, now on the other image here, we said quantization is basically interested in intensity. Now we have this intensity bar here, and at the bottom we have black. Then as we keep on increasing, then the intensity gets to white. So this representation in quantization, where we have white, it means this is the highest intensity. And where we have dark, this is the lowest intensity. That is exactly what is shown here. So every point of this image is represented in its respective color map. So the color map here helps us to now represent this image in a quantization. Now, the next thing that you're going to look at into is now on the same output that we've gotten, and now we'll represent it now on two images. One on the right is the quantization, the one on the left is for sampling. So A is a continuous image projected to a sensor array, while B is now the result of image sampling and quantization. Now, we have this image using sampling as well as quantization. Keep in mind, sampling refers to coordinate values, while quantization refers to intensity values. Now, what are these values that we are having here? Now, when the coordinate values are at 32, so these are lower coordinate values, then we see that this is the image that we get. Now, as we increase the coordinate values, then the image stops being blurry, and starts to increase in terms of the quality. The clarity of the image increases. So at 124, 128, then the coordinate values, that is, we are getting the coordinate values at 1.28, and this is the output we get. As we keep on increasing from 128 and double it to 256, this is what we get. Again, by doubling the coordinate values, we get these are now 512. And you can see as we keep on increasing the size of these, coordinates, also the image clarity increases. So it makes a lot of sense why we have these two parameters, one for sampling and another one for quantization. And in sampling, you see as we keep on increasing the coordinate values, we get that there's a significant increase in terms of the. Now, coming on the other side, on the right-hand side, now we see quantization. Now, quantization basically deals with frequency. Now, if you can remember the color map I showed you in the previous diagram, we had black at the bottom, and then as the color map keeps on changing, we find now we get to gray, we get now to light shades of gray, and then finally we get to white. So in that aspect, it means that when we are at 1 bit, so this 1 bit is just used to represent an intensity. So if the intensity is at 1 bit, then it means that the image is less significantly clear. But now as we keep on increasing, it stops being unclear and now starts becoming much more visible. So you can see that is what happens until you get to the 8-bit. The 8 bits means that now we are at a higher distribution, and now we are getting very much clear image. So in this case, we are using intensity on quantization and sampling with coordinate values. Now, having described what is a digital image, it is also necessary that we describe this image in the form of an equation. Okay, so we can think of an image as a function f. Okay, so what is a function in your programming? So a function is any operation that is applied to a class, and from that function it can be able to manipulate. It can be manipulated using the arguments. So it means that by using that function and supplying some arguments, then you can get a different result. So in that case, it means that if f is the function from r squared to r, so you can also say that f into x comma y, where now x comma y refers to the coordinates or the axis values on the vertical axis and value on the horizontal axis. So this will give us the intensity at position x comma y. So if we are representing this image by sampling, by getting the value x comma y, it can be used both as a coordinate and also the intensity at position x comma y. That is why it is very necessary to label it as x comma y. Now, moving further, so we expect the image only to be defined over a rectangle or a finite range. Therefore, we can say that the function f can be given as a comma b multiplied by c comma d. So the product of these are just position within this rectangle that we are talking about. So an image can be represented on a rectangle or a definite or a finite exact location. That is why we are using this now for locations. That is a comma b, and c comma d. So this one now gives us the result of 0, 1. So this 0, 1 means that this is the range in which the output can be obtained. Now, further on, we can say that this color image is just the 3 functions that have been pasted together. Now, what are these 3 functions? These 3 functions are vector valued. Whenever you see a vector, just know that refers to a matrix. So if it is a matrix, then we need to have rows and columns. So in this case, the image that is f into x comma y, where we have said x comma y is the coordinate values or the position of the intensity values. This one can be given by 3 color channels, that is red, green, and blue. These are the primary colors that forms an image, and we can now be able to see red in this image is represented by these coordinate values. Green is represented by these coordinate values, and blue is represented by these coordinate values. So these coordinate values, or sometimes we refer to them as vectors, these vectors of RGB are what forms a colored image. So this colored image can also be termed as f into x comma y. Now, given that we have said image as a function, and these functions we've now mentioned the RGB, the same can also be represented by this. So we have this image as our original input, and then we now try to twerk this input by now checking the image at different range of values. So you can see that if we now try to alter these functions, that is the value of x and y, then you can see that the image starts to get distorted. Okay, so that is what brings about now this result. Now, moving on, we now get to what is a digital image. So we've mentioned the introduction. Now we are going to look at the fundamentals. Now, this image, digital image, or sometimes known as a discrete image, is a representation of this image in the form of a sample and quantized. Sample said it is a coordinate, that is the xy, and that is the 2D space on a regular grid. Then quantize is intensity, so that is the nearest integer value. So if our samples are they are far apart, or they are far apart, we can write this as f into I, comma j, which is now given by now the quantization of now the product of f into change in I, comma change in j. I and j are just the intensity values in x and y axis. So when we do quantization, we're just trying to see what is the change of now I and the change of j along the x-axis. Now we can represent that using now this matrix. So we have I and we have j. So you can see now this is the change that we are talking of. As we move from 62 to 79, that is a change in j. As we move from 79 to 23, that is a negative change. Then further, that is a positive. As we keep on moving to the last end, which this image can be represented on a grid. Similarly, the same thing occurs on the other axis, that is I. Now let us look at what is image processing. Image processing typically define an image G in terms of an existing image F. Now, this is very necessary, and I want to understand it. You see, whenever you've captured an image and you've stored it in the memory, take that one as your original image F. After that, you want to beautify this image so that it looks very much beautiful. You change the color intensity, the contrast, maybe you add some filters, and then after that, the software gives you an option to download. When you download it, you get a new image. That new image is what we know of. So after the processing, you'll now have two images. First one is the original image. Second one is the processed image. So the original image is given by now F, and now the processed image is given by G. So that means we can represent this G in the form of an equation. So we can transform either the range of F. That means the input, the output that you're getting after now processing or filtering G into X, Y, where now this G is the new image with coordinates X, Y, and it is produced by applying a transformation. This transformation is not those filtering that or those beautification you are applying, and you are applying on the original image. That is what you need. Or we can also say that this new image, filtered image, or this processed image can be given by the change of the change of F. Now that is the image, and then we apply the transformation on the x-axis, and then that is putting in mind both the x and y-axis, comma the transformation of y along the x and y-axis. So these are the two ways that you can perform image processing. Now, having covered that point, now we are going to look at what are some of the application areas in which you can be able to perform this, the application as well as the research areas in which you can perform image digital image processing. The first one is on document handling. So if you go to the bank and they need to check if a document is genuine or fake, then they will use these techniques and algorithms. So also for signature verification, they will try to verify if the original owner of that check by checking on the signature. Also try and put your signature so that they can see if it is a match. Also on biometrics, we have iris, we have face, we have palm, we have fingerprint, we have voice, and also we have on text, handwriting recognition. So all these are examples of biometrics in which digital image processing is applied. So this is an example of how this fingerprint verification is done. So we'll first enter the fingerprint on the machine. Then the machine will collect that fingerprint and try to find a match. There are so many n matches in the database. It will try to find which one is the best. And if it is the best, then it will return a yes, you are permitted. Either it will say attendance is recorded, or if not, it will reject. If there is a match, that is a one-to-one match, then it will return a yes. That is performed by extracting information from the database. So we also have fingerprint identification research at UNR, so where we perform this fingerprint identification. Also object recognition, where we are able to identify different objects. Also, we can be able to check, in this case, like indexing of an object. So indexing, it means that first we must capture the object we want to recognize, save it into a database, and then capture the different shapes of this object. Then after that, if we now show this object in any shape or in any direction, the system can be able to recognize because there is multiple angles in which the image was captured. So we also have, this is the same thing for image object recognition, where we now use color and texture to check it. Also for target recognition, this one can be used in defense, either in the Army, Air Force, or in the Navy. Then we have interpretation of aerial photography. So this one is very necessary whenever we are doing image registration or computer vision, where we want to identify different objects in a scene. So maybe you can identify this is a car, this is a house, this is a factory, this is a lane, this is a tree. All these can be used for interpreting what is present in a scene. Also for autonomous vehicles, which can be used in the land, water, and space. So this one is very necessary. They need scientists and other researchers in difficult exploration problems. Also in traffic monitoring to check which users are overlapping and who are they, what time of it, which place and date. All this can be applied by digital image. Next we have on the other one, which is face detection. So on face detection, it is also necessary to detect different faces in a crowd. So this is it. If you want to detect a face, first we must capture the faces of those people we need. That process is known as supervised learning. And then after that, we'll be able to now bring a new face and see if the machine can be able to obtain an exact match. This is the same of the face detection. This is the facial expression recognition, where we can be able to express different 7 expressions, that is anger, sadness, fear, disgust, happiness, and anger. All this can be able to be described. Face tracking. So face tracking, we want to see if there's a change in a face, that is to check if how a person has been able to grow old over a period of time. So you can be able to see the changes that have been taking place. So hand gesture recognition, where we can say like, this is a 5, this is one is a 1, this is a sign that says, okay, this is 1, this is 2, 3, 4. All these are hand gestures. And for that to be done, the system has first to be trained to understand that this, if I do like this, I mean this is a 5. And if I do like this, then this is a fist. If I do this one, this is 1. And this one, this is 2. So also it can be able to use it for sign language. If I do like this, come, then it should be able to see that, to recognize that if this symbol is done or this sign, it means come. Or if someone says like this, it means he or she is refusing, or is warning of not to attempt that activity. So all this can be done on digital image processing under an area of machine learning known as computer vision. So we also have human activity, where we can see the activities that are going on between different groups of people. Also for medical diagnosis, breast cancer diagnosis and skin cancer. Also for image morphing. Image morphing is to take an image of a particular object and try to put it on an artificial environment. So in this case, we are taking the image of this person, the face, and putting it around the image of a baboon. So he will look like a baboon, but he's a human. Or we can take this face of this human, this baboon, and place it on the image of a person. And this baboon will appear like a person. So we can also insert artificial objects into a scene, that is morphing. And these are the references that have been used to create this lecture. Now we'll come to the MCQs. So first question is, a Quanta's image is digitized at points. So we have either random, vertex, contour, or sampling. So here the answer is random. Then the next question is, the transition between continuous values of the image function and its digital equivalent is called as a, this one we already mentioned what it is, then you can refer to the PPT. So the third question is, to convert a continuous sensed data into digital form, which of the following is required? So in that case, also mention the same. The fourth is, the expression S is given by TRT. So what is the answer? So here, of course, the answer is given to you. Then the next question is, pixels are digital numbers that are composed of, so either colors, intensity levels, dots, or bits. So that one requires also to have an understanding of what is pixels. And which of the following is an application of digital image processing? Morphing, face tracking, hand gesture recognition, all of the above. So you know the answer. Representation of image in time and space, as mentioned, what is it? And the resulting image of sampling and quantization is considered a matrix of real numbers by what name the element of the matrix is called. Also, among the following image processing techniques, which is fast, precise, and flexible. So optical, digital, electronic, and photographic. So the last question, what is a pixel? So these are the different options given. And so this is what we've been covering in today's class. And I believe that we've been able to understand what we've covered today. And now in the next class, we'll now be able to understand what are the components of the image, how can we be able to represent an image in both different forms, that is in the spatial domain and the frequency domain. We'll be looking at this in the next class. I believe that you'll be able to understand as you have understood in this class. So until we meet again, have a nice time, and you can refer to this lecture that is shared for further reference.